The microphone. Hello. Okay. Is it good? Constantina? Oh, hello. I feel now I have a power. Okay, cool. And we still have 2 minutes. Constantina? 2 minutes. Wow. Yes, let's go. Hello, everyone. Welcome to problem-solving session of DDCA. So in this session, we will solve questions from Spring 2023. I get how many questions? Like 10 or something? Don't count on that. Okay, so I'll start with ISA versus microarchitecture. It will be a rather quick one. I'll need to choose the color first. Okay, I'll choose red. So the question is, circle whether each of the following is an aspect of the ISA or the microarchitecture. So we have 15 questions here, and you're going to choose which one is like ISA or microarchitecture. For example, let's start with the first one. The width of the immediate value in the add instruction, which is defined in ISA. So we select ISA here. And the second one, the algorithm used by the ALU to perform multiplication. So this has nothing to do with ISA, and this is defined in the microarchitecture. So the correct answer is microarchitecture. A number of bits required for indexing the source register of a store instruction. So this is definitely in the instruction set architecture where we define these things. And so that's why it's ISA. And number of entries in the L3 cache. This is a design choice, nothing to do with, again, ISA. So it's microarchitecture. And the data cache organization, for that, it's the same, again, microarchitecture. 6.1, support conveying prefetching hints to the hardware via compiler. So this is ISA again, not again, this is ISA, and available data types for arithmetic and logic operations. And this is ISA. One example could be like RIS5I, which is just for integer, RIS5I, F, M, and floating points and so on. So this is ISA. And the cache coherence protocol in multi-core processors, again, a design choice is microarchitecture. And the width of the data bus between processor and main memory, again, microarchitecture, this is not defined in ISA. And the memory controller's memory request scheduling algorithm, again, microarchitecture. 11th question, instruction encoding for data control flow and branch instruction. Again, instruction encoding, it says. So this is defined in ISA. And the design of the register renaming logic. It is, again, the design shows that microarchitecturally done. So again, microarchitecture. Number of instructions decoded per cycle in super scalar processor. So this is based on your width in the microarchitecture. So again, microarchitecture. And L2 cache miss latency. This is not defined in ISA, so this is basically depend on the protocols that you have, how big your L2 or the other, let's say, caches you have. So this is again microarchitecture, and the width of the program counter is ISA. So that was a rather quick one. So yeah. I hope it will be quick for you as well in the exam. Thanks.
Yes. So the next question is the pipelining question. This one is a relatively long question, but it's very easy, actually. So let's get started. 1 second. We need a lot of colorful pens. It would help you in the exam also, if you can use it. I don't know if you can use it. Maybe you can check that. Okay, so... Okay. Here we have a code listing which contains a piece of assembly code, and table 1 presents the execution timeline of this code. So right now we don't need to understand at this point what this code does, but it's described in this comment side if you're struggling with the instructions. So everything is basically explained in this part, like line by line. And next we have this execution timeline, which shows the pipeline stages that these instructions are in each clock cycle. For example, in the first one, we see that the first instruction is fetched, and then it goes through the pipeline and so on. So the question says, use this information to reverse engineer the architecture of this microprocessor to answer the following questions, and answer the questions as precise as possible. If the provided information is not sufficient to answer a question, you can answer unknown and explain your reason clearly. And the first question, the first part of this question is, it asks you to list the data forwarding paths between pipeline stages. So the data forwarding paths, basically, they enable you to use register values that are not yet written back to the register file. So you can basically forward the result of an instruction early to the next instruction if the data forwarding path is implemented in the microarchitecture. So for this part, we first need to identify which register values are used before they are written back. And to do so, we first need to understand the data dependencies. So I will just mark some of the registers that are used throughout these instructions. So here, we first have R1 that is written. So here you can see that the value stored in the address X is stored in register 1. So this is our first register. And then I will use different colors for different registers. So here we have also R2. And here on the third instruction, you can see that R1's value is used to calculate R4's value. So you do a multiplication, you multiply R1 by R1, and then get R4. So you can see that the register's value is used this way. And the next one, we again have some R1 here as the input and as the operand, and also we have R2. And you can also see that, okay, we need more colors. You can also see that now we will write back to R1. The result of this instruction, this multiplication will be written back to R1, which changes its value. So I will just mark it with another color. And next we have an instruction with R4, R5, and R6. These are not related to the earlier ones. You can also think that, okay, R4 was written here. Does that create a data dependency? The answer is no, because you basically overwrite the result in the instruction 5. So it's not read, it's written again. Okay, so let's look at the sixth one. Again, we have R2 as the operand, so that we mark. And now, okay, I ran out of colors. Let me see. Maybe I can use this. Okay, so now we have R4. This is slightly a different color, but you cannot tell probably. It's okay. And the value was written in the instruction 5, and then we use it here. And after that, we again have R1, which is here. Thank you. I think this is, it's fine, but let me mark it differently. Okay. So, and then this is like the last instruction that we will talk about register dependencies. Okay. And based on these, now we will check the pipeline stages and see how these are read before, if they're like read before the write back stage. So let's start with the first one. As you can see, the first dependency that we will talk about is here, which is reading R1's value. And this instruction was fetched in cycle 3 and then decoded as cycle 4. And then we wait for the result of the first instruction here to be ready. And after that, you can see that we immediately go to execution stage without waiting for the write back to happen in this cycle 7. So this means that once the value of R1 was ready, we forward it to the first execution stage for this instruction to continue execution. So this shows us a data forwarding path from E3 to E1. And this was coming from R1 value is forwarded. You can also say that in which cycle, like cycle 6 shows this. So that would be, make it easy for us to understand your reasoning. So that's good. And after that, let's check the next instruction here. I'll show you with this. With again, R1, we see that after this instruction was decoded, it moved on to executing immediately. I will show you with a different pen. You can miss this one, actually. This is a bit more tricky because basically we saw this like data forwarding path from E3 to E1 for R1. This time, the same value is forwarded to E1 from the this stage, stage memory. So again, we are not waiting for write back to happen. So this, we'll write, oh, sorry, M to E1, again for R1 value. Okay, and next, we will again continue with the instructions here. You can also consider R2, but this is the same forwarding path as the instruction 2. The result that will be written to R2 is in E3, and then it is forwarded to E1. And that's the same forwarded stage as we showed earlier. So I'll just, so it's like an example of this again. Okay, so let's continue. Here, in this part, we already evaluated this. So in this part, we don't have a data dependency, so I'll just skip it. And in the next one, what we see is we have a dependency for R4. And when this instruction was fetched at cycle 7, decoded next, and then waits for a couple of cycles, and after a while, it is executed in this stage. And the value of R4 was available here. So again, you can see that this is the same data forwarding path. Okay, so Next, we have this instruction 7, and here R1. You don't need to really consider a data forwarding path for this one, because when this is executed or decoded, R1's value was already written back in this stage. So it's like an early stage already. So you don't need to consider any data forwarding path for this one. So another one that is sort of hidden in this part is that when we consider the instructions, you can see that in this instruction 8, we do an execution. We calculate R3 based on R1's value, but basically subtracting 2K48 from the R1's value. And then after that, we have a jump instruction here. And this jump instruction, what it does is basically it jumps to the label L1 if 0 flag is not set. And you can see that the previous instruction sets this condition flag. So it depends on that. Basically, it depends on the result that is written to R3, or basically the result of this computation. So to be able to execute that, that dependency needs to be solved. And here we see that this instruction is fetched at this cycle 11 and then decoded, and then waits for a couple of cycles and executed at this part. So you can see that after the execution is done, you don't need to really do this because that's not the part of the execution. So basically at this point, the result is forwarded to the condition register, and then there's one data forwarding path from E3 to condition registers. And after this point, we don't know anything else because these are the instructions that we see, and this is the pipeline or like the timeline that we see. And if there are other data forwarding paths, you cannot understand from this timeline. So this is the correct and complete answer. Is there any questions? Yes. Mm-hmm. In this particular question, I guess we assume that the data forwarding path is from the previous cycle to the next one, but it should be clear from the question that what we should assume. Basically, maybe you saw a different version of the same question, which has a different code, but then it has another assumption. You can write that, okay, this is my understanding of the question if it's not written there, like this is what we assume. And then we will evaluate it the same. So it doesn't really matter unless, basically, unless you show wrong data dependencies. If the data dependencies are correct, it should be correct. Okay. Are there any more questions? Okay. Now, then let's move on. Let me find the rest of the question. Okay. So in the next part that I will show like this, in B, the question asks, does this machine use hardware interlocking or software interlocking, and explain why? So when we look at the timeline here, we don't see any bubbles or knobs inside this like instruction sequence, right? This shows us that the machine itself, the microarchitecture, detects data dependencies and then stalls the pipeline stages, which is in hardware, which is done with hardware interlocking. So the answer is hardware interlocking. And we would expect you to write the same explanation, but I will not write it in the interest of time. Okay, so next, In this part, we are doing a little bit more like reverse engineering again. So for the rest of this question, assume the following: X is 4, Y is 2 in the code listing 1, and branch predictor always predicts correctly. The machine uses hardware interlocking, and now this part of the question will give you a state based on this. So at a given clock cycle t, the value stored in R1 is 1024, and the processor fetches the dynamic instruction n, which is multiply R4, R1, R1. And I'll just show you the code and the timeline as well for this. Okay, maybe I'll just... Yes. Okay, so calculate the value of t, the clock cycle of the given snapshot, and show your work. So here, what we know is that at this snapshot, clock cycle t, the dynamic instruction that we are fetching is multiply, which is multiply R4, which is this, this instruction. And then what we know is basically we started executing with x equals 4 and y equals 2. And now basically get this value, we need to first look at like the general timeline a bit more. 1 second, so. Okay. So let's look at what this code does at this point. It starts with moving the values of x and y to R1 and R2. At this part, you can see it, right? R1 becomes 4, R2 becomes 2. And inside the loop, so this is like a loop. As you can see, there's a jump to the start of the loop. The first instruction does the following. So it writes to R4 by multiplying R1 and R1, which is 4 multiplied by 4 and 16. Is that correct? Yes. And then in the second part, it updates R1 by multiplying R1 with R2, which is 4 multiplied by 2, which is 8. And then we have an addition, but this is not relevant to the code because it uses basically a hint for you is basically it uses some unused and undefined registers. So you can maybe not think about it in this part. It's not important for the loop. And then next we have another instruction, basically changing the value of R5, which is again not relevant to the question. And after that, here we have a calculation for R3. And what it does is, it basically does this calculation and checks, and next it checks if R3 is 0. And then either continues or jumps to the start of the loop. So here you can think of this as like a condition. It checks if R1 is, if it reached to 2048, right? So this is like a simple code that basically multiplies R1 with R2 repeatedly inside the code until it reaches 2048. And basically what we expect is that with these starting values, it should execute the whole loop a couple of times and then reach this clock cycle t. And what we know is that at that time, R1's value is this, 1024, which then we can calculate how many times this loop has iterated, right? So we start with R1, 4 in the initial part. And then inside the loop, we have R1 value that is equal to 8 at this point, the first iteration. And in the second iteration, it should be 16. And then it goes until R1 equals to 124. Okay, I guess at this point you can understand how many times you need to iterate this, but let me tell you, it's basically, 1 second. Maybe you can also say that. I see someone whispering. basically it should execute like 8 times. And based on this, now we can calculate what t is. And now we have to look at the timeline to check how many times you need to execute this loop. And let me do it 1 second. So, okay, let's look at the first iteration of the loop, which is here. You can see that. After this point, since the branch prediction always brings the correct instruction, what you will get is another multiply R4, R1, R1. And this makes this part from instruction 3 to 8 basically the first iteration, right? So you can now see how many times this, how many cycles you need to execute this by completing this part, maybe. And then it's 17, 18, 19. Okay, then when you complete this to get the next instruction, what you have is this instruction will be fetched at cycle 12 and then decoded. And since it will use the R1 value, you need to check the data dependencies again. So the last time the R1 was executed, it was written back here. And then we don't have any data dependencies. Next, we will look at the stages. Since the execution 1 stage is busy with, oh, okay, this part is wrong. So we cannot move on to decode because this instruction stays at decode at these points, right? And then when it's ready, we will get the decode stage and then execute and go on. So you can see that the first loop that was fetched at this point, and basically the next fetch is here. It takes like 9 cycles until the next fetch. And here is a little trick, basically. That's different than the next iterations because we will have basically an extra 1 cycle here that is coming from this stall because this is different than the first fetch that is here. So maybe this part was a bit confusing. Do you want me to explain it again? Okay, so we first looked at the first iteration and then calculated how many cycles it takes. And then we've checked the next iteration by starting the instruction that is basically our snapshot instruction to understand if something changes in the second iteration. And at this point, what we see is the execution of the first iteration of this instruction and the next one differs because we have 1 more stall in the decode pipeline stage. So this is why the next iteration will have 1 extra cycle compared to the first iteration. Is that clear? I see some nodes. Okay, so this means that, okay, first we have 2 cycles coming from initialization, 2 cycles, and then the next loop iteration, which is the first loop iteration, will take 9 cycles. And then, okay, did I do something wrong? Okay, so this is 3 actually, because we are calculating like this. And then the next iterations, which are like 7 iterations, because we counted the first iteration here, will take 10 cycles. And after this point, you get this number. Okay. Now, okay, then let's move on to the next part. Next, the question asks, calculate the value of n. N was the number of, basically let me show you here. So n is defined like this. This is like the count of the dynamic instructions at this point where we fetch this instruction. So basically what we are looking for is, okay, I'm showing you the result actually. Yes. Okay, so what we're looking for is basically here we have our instructions. So this is like the first fetch of the instruction that we're interested in. And this is the second fetch. And after a while, we will have like the third and so on, like for 8 iterations, we will have in total 9 fetches of this instruction, or 8. It's not important. Basically, we will try to get this, like the count basically here and okay, so we are interested in this number. We can calculate this based on the number of iterations that we have, which is 8. The first instruction is the first iteration of this instruction is the dynamic instruction 3. And then the next one is 9, because we have 6 instructions in between those. This is like the loop invariant, or basically the number of instructions that you have inside the loop. And we will continue like this. So we will add like 6s and 6s and so on. And basically, what this gets us is at the end of 8 iterations, we basically will have, sorry, I'm checking if I missed something. No. So since we have 8 iterations of this, we multiply it by 6, the number of instructions inside the loop, and we will have 51 as the n value. So n is 51. Was that clear? Yes. Basically, I use this timeline to, basically we have the initialization phase, and then it's like the third instruction that we have. And then after a while, we will just fetch it 8 times until the last one. Is that clear? Two plus 8 times 6. And then, so after 8 iterations, we are patching the new one that is starting the next iteration. Like it's like actually the first instruction of the 9th iteration. So you get +1 based on that. Okay. Okay. So in this part, now, okay. Now we are looking at this. The question asks, like, lastly, like calculate the total execution time of the assembly code in code listing 1 and until the completion in terms of the number of clock cycles. And it asks us to show our work. So for that, we need to figure out when this code ends. And when we look at the code itself, we see that basically this jump always goes to label 1 unless the R1 value is equal to 2048, right? So the last update of the R1 value should be making it 2048. So let's again write like what changes in terms of like iterations. In the first iteration, after we execute the first iteration, we get the R1 value of 8, and then it is multiplied by 2, and then it is again multiplied by 2, and then we go until the end, and at the end, the last update should make it 2048, right? So you can see that this is like, and then this is this, and we basically see that, yes, we basically see that we need to iterate like 9 times to get to this point, right? Okay, and let's look at the timeline to get the total execution time again. So here, what I will do is following. This is getting a bit crowded, but let's see if I can make it clear. Okay. Yeah. Here until the end of the first iteration, basically this is the last write back within the first iteration, right? This is like the last instruction, and then it's written back at this clock cycle. So we can also use there are two ways to do this, and I'm confused about which one to follow. So let's use this calculation. So here, what we did is we calculated the time it takes for us to get until the second iteration of the loop. So with also including the initialization, it takes 12 cycles. And after that point, we need to execute the loop 7 times. Is it 7 times? I'm sorry, this is getting a bit weird. Yeah, so we need to calculate, we need to do the loop 7 times. So plus 12 plus 7 times 10 will give us the execution time. Oh, I messed up. I'm sorry. 1 second. Yeah, okay. Let's move on. Let's basically use the second version. So, okay, this is like the end of the first iteration of the loop, and it takes us 19 cycles. And then after that, since we use the we include the first iteration here, we have 8 more iterations to go for, and then it takes 10 cycles as we calculated in the previous parts. And then after that, we need to also execute 1 extra instruction, and then that will like execute at the end of the execution of the whole code, and then we will have 100. Sorry about the mess. Do you want me to recap? That was fine. Okay. All right.
Yeah. I think there's more shots all underneath it. Okay. Sure. Yeah. Right. Yep. Right. Okay, so I will deal with 3 questions. We will go in a different order than the paper. We will go with memory potpourri first. Then we'll discuss finite state machines and vector processing. Let's do memory potpourri first because the previous question was a bit difficult. Let's start with something simple. So the question is as follows. Read the following statements about memory organization and technology. Circle true if the statement is true and false otherwise. And yeah, you lose 2 points if you have an incorrect answer. So you want to be sure here. The first one, a main memory access typically has larger latency than a register file access. This is true, particularly because of the long bit lines and the distance from the core.
SRAM is commonly used as main memory in modern computers. This is definitely not true. Use DRAM as main memory. DRAM cell requires larger power to store data compared to an SRAM cell. So this is two components to it, the static power and the dynamic power. The SRAM cell requires a higher static power because of the larger number of transistors used to build an SRAM cell, and this generally outrights the dynamic power. So this is incorrect. All right. Reads are faster than writes in DRAM. This is not true. Generally, both of them have similar rates. So this is false. Reads are faster than writes in phase change memory. This is true because in phase change memory, you read data by measuring resistance, but to write data, you need to change phases, which takes longer. So this is true. A bit line in a DRAM array connects all DRAM cells in a DRAM row to the row decoder circuitry. This is incorrect. So the row decoder is usually something like this. On the left-hand side, it's used to open up a row, and you have bit lines running vertically. So the bit line is really connecting all rows across essentially all rows in the DRAM bank, and they're connecting it to the sense amplifier. So this is false. Next one, using virtual memory reduces the memory access latency. Using virtual, this is not the motive of using virtual memory in the first place, and some would say that you would increase memory access latency when you use virtual memory. So it's false. Phase change memory is non-volatile, and this is true. You don't lose data, you don't need to refresh. Next one, if a hypothetical service system is not constrained by chip area, memory cost, and energy consumption, PCM would be the best memory technology to use in that system. The problem with PCM is write endurance. After some number of writes, your system, your memory is no longer reliable. So by that metric, well, you can't quantify and say that PCM is the best memory technology in that scenario. So this is false. If you have a program, so a program with a streaming memory access pattern, this would lead to very high memory locality in the last data level cache. A streaming memory access pattern basically means you access a different element across different cycles, different timestamps. This is not temporal locality. Temporal locality is you access the same element across different timestamps. So this is false. In DRAM, accesses to different rows in one bank can be serviced faster compared to accesses to different rows in different banks. This is false. If you have requests going to a single bank, so look at this picture here. If you have to access data in different rows, you need to close a particular row and then open another row. And this is longer than, let's say, having another bank where you access a different row. Because you can have these rows open parallelly using bank parallelism. So this is false. A TLB is a specialized instruction cache. This right away is incorrect. It's a translation loci buffer. You cache translation entries here, not instructions. Virtual memory simplifies software design. This is 100% true because you no longer have to deal with physical addresses. You see an infinite memory space, and you don't need to worry about what these values are. The infrastructure, the computing system handles this all behind the scenes. A page fault happens when the TLB does not contain the entry needed by an instruction. This is false. It happens when you don't have the translation entry, essentially when you don't have the entry that converts the virtual address to the physical address. So this is also false. A fully associative L1 TLB that only stores 4 kilobyte virtual to physical mappings and has 1024 entries can cover up to 4 megabytes of memory. This is true. You basically just multiply these numbers because you have the V2P mapping size and the number of entries. And therefore, you can cover up 4 kilobyte times 1024 number of, let's say, physical addresses. For this physical addresses, and this basically evaluates to 4 megabyte, and that's true. Any questions up to this point? Okay, looks like this was very clear. Good. Let's then do a slightly more difficult one, compared to the memory potpourri at least. Finite state machines. So we have 2 questions here. First one is to simplify an FSM, and the second one is to design an FSM. On simplifying an FSM, I hope this is very visible. Is this visible enough? Or okay, cool. So you're given the finite state machine of 1 input, 1 output digital circuit design, and yeah, you need to answer some questions based on this state diagram. The first one is, can you simplify this particular state diagram and reduce the number of states? So currently we have 4 states, A, B, C, D. And if you can, simplify to the minimum states, and you should explain every step of your simplification. You draw the simplified state diagram, and if you cannot, you should explain why. Right off the bat, one thing that you can notice here with each of these states, A, B, and D, they have very similar input-output patterns. For example, let's start with A. And by the way, the nomenclature here is the left-hand side of the slash is the input, and the right-hand side is the output. I suppose this is very clear from the lectures. For A, when you see 0, you output a 1. When you see a 1, you output a 0, essentially inverting the input as the output is basically the invert of the input. This is the same for B. When you see 1, then you go to 0. When you see a 0, you go to 1, and the same also is true for D. This is also true for C. So essentially, you can come down to a single state and perform this logic. Essentially, what you really want at the end, I'm not going to go step by step here. I can go, the solution describes it step by step. Okay, let's go step by step. So let's say the current state, I will describe it in the format that it's described in the solution so that you can follow if you couldn't follow it from the state diagram. So let's say we have the state transition table as follows. Okay, so let's have the states for A. Let's say you have an input 0. The next state is A. The output is going to be 1. Let's say you have the input 1. The next state is going to be B. And your output is going to be 0. If you were to do this for all the states, you notice exactly what I was describing. Let me quickly populate this. So B on 0 goes B on 0. I'm missing something here. Yeah, B on 0 goes to A. B on 1 stays in B. And the output here is going to be 1, 0. Let's fill up the outputs. And for C, when you have an input of 1, you go to A. And when you have an input of 0, you go to D. And for D, when you have an input of 0, you go to A. And when you have input of 1, you go to B. For now, you can forget about C for a second, or for a moment at least. Let me try this. Okay. What you would see is for each of these states, A, B, and D, the next state is the same. It's A and B, and the outputs are also the same. So at this point, how you can rewrite this diagram is the following. You have C, and you start with C on a reset. And let's say we have some state X, a new state X, which basically abstracts away A, B, and D. And what happens is C goes to A, or in this case, X, when you have a 0. It goes to, again, this new state X. Am I doing this correctly? Oh, actually, it doesn't matter to draw this out. You could just use don't care conditions. Let's do that. And you can interrupt me anytime if you have questions, or if I don't explain this well, which is also fine. And you have the output, okay? And we saw that we can decompose this down to 2 states. Let's say the new state is called X, okay? And we retain the C. And you have your inputs, 0, 1, 0, 1. When you see for this state X and an input of 0, you stay in the same state, and you have the output 1. Your output is inverted for all cases. Let's fill that out first. And now when X sees a 1, it also goes to X again, right? Because we see that the states A, B, and D are pretty much the same. They're equivalent. C, when it sees a 0, it goes to A. In our case, that's X. C, when it sees 1, it goes to D, which is also X, right? So you can see that always the next state is X, irrespective of what the input state is, which means that you can rewrite this as following. If you have the reset, you go to X, and you always go back to X, irrespective of the input. The only thing that you do here is you invert the input. To compute the output, you invert the input. That's the FSM, at least the first part of the question. Any questions here? So it's very clear again. Perfect. So the next one, we have a little bit more fun of a question. So you're supposed to design a more FSM, and the definition of a more FSM is that every output that you generate will only depend on the current state. Essentially, the output is only a function of the state. It doesn't depend on the inputs. If it was a mealy FSM, it would depend on the state and the input. The state machine would have just one input and one output. And the goal of the FSM is to detect a stable transition in the input signal from a repeated 0 to a repeated 1. And the definition of a repeated 0 to repeated 1 is this one right here. So the output should be logic 1 only when the input sequence of 0, 0, 1, 1 is observed. So you have a repeated 0 followed by a repeated 1. And in all other cases, you see an output 0. Then you also have the information that when the circuit is reset, your state machine should assume that the input signal has been high for a long time. This will be key piece of information when we start drawing the FSM, but for now, let's keep that information as something that we have to use. Draw the state diagram and explain why this works. And your state machine should use as few states as possible, and each state should have a precise definition and output. You can see that you have 4 values here. 4 bits, which means that you can have up to 16 states, correct? This is the brute force solution, and this is not what we're looking for. We're looking for the fewest states possible. And what you will notice is that you can think of this in a sequential manner. So let's start with putting up all the states that we can think of, and we will come to the solution. Clearly, we need the state that identifies 0, 0, 1, 1. So clearly, one state is going to be called, let's call it as 0, 1, 1. Let's stick to the nomenclature in the solutions. You get to this state And of course, when you're at this state, because this is a Moore machine, you have an output 1. And we write the output as part of the state because, again, it's a Moore FSM. You can only get to the state when you've seen the sequence, and I will write this here as scratch, when you've seen the sequence 001 in the recent past. If you've seen this sequence, it doesn't matter what exists here or here. If you've seen these 3 in the past, you see another one, you can get to the state. So let's introduce that state, and we call this 001, and here is going to be an output 0, and you get to this state when you have an input 1. Good. If you have to get to this state, you need to have seen 2 zeros, which means you need SX, and let's call it 0. The output again is going to be 0 here, and we will have a 1 as the input to get there. What else can we build from here? This is when this becomes very useful here. So when you have a reset, your machine should assume that the input signal has been high for a very long time, which means that the last input that you see is 1 when you enter the reset stage. So definitely one state has to be something of the sort of this. And this is what you enter when you have a reset signal. So this is, let's say, the 4th state. What else can we fill? Let's look at S0011. What happens when I see a 1 after this or a 0 after this? If I see a 1 after this, after, let's say, 0011, if I see a 1, this is no longer an interesting pattern for us because we can't get to 0011. And if you see 00110, again, this is not an interesting pattern because what you want to see is 0011 in the sequence. So in the case that you get 1, after this, you go to the reset state, the state that you enter, the X6X1. You also need another state, which is corresponding to this one, where let's say you have a 1 and a 0 at the end. And this is what we will create here, the SX10. Is that correct? That's correct. And this will be, again, an output 0. And you get here when you have an input 0. Has everyone followed it until here? If not, you can ask me. Questions? Okay, good. All right, so we have these states. And now our job is to complete the diagram. At this point, when you see 1, 0, if you see a 1, you go back to this state because this is the last one, right? So this is where it goes when you have a 1. If I were to see a 0, then this sequence now becomes very interesting to me because you'll have a 0 and a 0 following it. So it goes to this state on a 0. We haven't handled what happens when you see a 0 here. What happens when you see a 0 here? Well, we're still on. We're still interested because if this follows, if the 0 is followed by another 1, then you can go to this state. So let's stay put here when you see a 0. Okay? We haven't handled what happens when you see a 0 here. So when you see a 001, and when you're in 001 and you see a 0, you end up with 10, which means this is the state you would go to when you see a 0. We've handled all possible scenarios here. Here, not here. We have only, well, we don't have any exit points here. So what happens when you have a 1? Well, if you have a 1, you are still locked in here, basically. You have the same terminating value. If you see a 0, then you go to this state because we've created a state for 10 specifically. And that's the entirety of the state diagram. If you can walk us through with your writing as to what each of these states mean, you will have full points. That's pretty much the FSM question. Any questions here? If you're confused about something, please ask me. Does not look like anyone's confused. Okay, so that's the second question. And now we move on to the difficult but very fun question. So for these kind of questions, what you want to be wary of is that the huge amount of text should not be looked at first. You should look at the questions. Maybe side by side would be helpful. So let's do this. So this is on vector processing. What you see here is your instruction set. You have an ISA for it. You have a bunch of assumptions. Let's not worry about the assumptions for now. So what you're supposed to answer is 3 questions, I believe. So the first one is, what should be the minimum number of banks to avoid stalls while executing these 2 instructions? So clearly we need to focus on what these 2 instructions mean. And calculate the minimum number of banks for every stride. We need to understand what the stride means here. Okay, these are the 2 things that we need to understand for this question. For the second one, translate the following loop into an assembly code that can be executed in the least possible number of cycles in the previously described vector machine. So you have this code, and we have an instruction set here in the main question. So they basically want us to unroll this, let's say, C program into this set of assembly instructions. And you've seen something similar in DDCA labs where you wrote assembly basically. But this is with vector instructions. That's the only difference. The third question, what is the number of cycles the previous code being this code, takes to execute in the processor that we describe? And again, you have some assumptions. Okay, so these are the questions that we need to know, or we need to solve. And for the first one, we need to understand what the VLD is, what VST is, and what do they mean by stride here. VLD. So VLD is described by 1 operand, well, 2 operands, VI, and the number A, which means something here. And its latency is 50. Well, it says 50 row hit, 100 row miss pipelined. At this point, this may mean nothing to you. And this is what the description of the instruction is like. Basically, so A is the address. So based on the address you give, you load the data from the address into the register VI, which you describe here in the instruction also. This for something similar for VST. Essentially, you store data that is in register VI into this location. But you need more information than that to understand what's happening. So let's scan the assumptions and see if we can find information. So we need information about VI, what that means. And what do they mean by row hits, row misses, pipeline, etc. So let's start and scan. We have something about VLD here. Do we have something else? We have some latency here. I think that, and the right registers, okay? Let's start with this. So there are 8 vector registers. You have V0 to V7, and the size of a vector element is 4 bytes. 4 bytes, 32 bits, doesn't matter. What else is interesting? This one, the main memory is composed of N banks. You have N banks in the main memory. They don't describe what N is. And each bank has a row buffer of size 64 bits, which basically would be 8 bytes, or in our case, 2 vector elements. Does everyone follow until here? Good. All rows in the main memory are initially closed. So you have to pay the row access penalty, basically. Opening of the row penalty, I mean. The memory is byte addressable, which means that you can access 1 byte at a time. Essentially, address A would correspond to vector element 0. Address +4 would correspond to vector element 1, right? because it's byte addressable and every element is 4 bytes. They're stored in a 4-byte line manner. The first element always starts at the beginning of the row. Great. This is also interesting. Vector elements stored in consecutive memory addresses are interleaved between memory banks. So we saw here that we have n banks, right? So, I mean, of course, they described further. So if you have a vector element at address A, it would map to bank B. A vector address at element a vector element at A4, A plus 4 would map to bank B plus 1 modulo n, essentially the next bank that you have in the set of banks. And n may not necessarily be a power of 2. This is additional information that you don't need to worry about right now, I think. Then they describe what the latency means. The latency of accessing memory is 100 cycles when you miss in the row buffer. This is what they're talking about here, 100 row miss. 50 cycles when memory request hits in the row buffer. And this is what this is. All right. And every bank has a single read and single write port so that each load and store operation can be performed simultaneously. You have one functional unit for VLD and a separate functional unit for VST. So you could, let's say, do them parallelly, but you cannot overlap them for different vectors. That's, again, described here. And then the last they describe about vector mask register, which looks like we don't have to worry about at the moment. Cool. And of course, stride, I think they don't describe here because it's part of the lectures. So I assume they assume that you're aware of this. But if you're not, stride really means what is the distance between consecutive elements that you access in your program. So if you access memory A plus 4, and then memory A plus 8, this is at a stride of 1. If you were to do this, is that right? Yeah, A plus 8, A plus 16, this is at a stride of 2. Okay, does that make sense? Okay, looks like it makes sense. Okay, so the question is, what should be the minimum number of banks to avoid stalls? Now, when you describe the minimum number of banks to avoid stalls, it means that you are trying to send a request to the DRAM in every cycle, essentially. You don't have stalls, and once you get data from the memory, you can issue another request. Essentially, the data path is not bottlenecked by memory accesses. And what you can think of here is try to start with 1, 2, 3, 4, 5, 6, 7, 8. Assume different strides and think about how many banks you would need. We know that this is the penalty that you pay on a row miss. And why we should consider the row miss penalty is because they describe that the DRAM is first entirely closed. All rows in the main memory are initially closed. Okay, so the first access is always going to be a row miss. And so let's say we have a stride of 1. Then the banks that you would access would be bank. Let's start with, how do we index it? Let me follow what they do here. Okay, let's start with 0. So you would access 0, 1, 2, 3, and so on, right? The memory access latency of this is 100 cycles because it's a row miss, which means that the data of this is going to come back at some point in the future, and that is at the timestamp 100. Which means that you can only send another request to the same bank at cycle 101, right? Therefore, if I were to have 100 banks, I could get away without incurring any stalls. Does that make sense? Cool. Let's take 2. So B is, we can start with 0, 2, 4, 6, 8, and so on. And at some point, you will have 100. And this is going to return back with data in cycle, again, 101. Well, you can send another request to this at 101, which means that after you do 100, you want to be able to request 1 again, so that you use all the banks that you have as much as possible. And then at cycle 101, let me write 100 here, somewhere in between, 1, and then 3, and then 5. So that you can, in cycle 101, this is cycles, in cycle 101, you can again go back and access 0. Is that correct? Maybe not. 0, 0, 1, 100, and then you start with 1 and 3, 5. You end up with, yeah, you need 101 as well, right? Sorry, I will do this again so that it's clearer. When you have stride of 2, you start with 0, 2, 4, and you go up, let's say, until 100. I'm arbitrarily choosing 100. At cycle 100 in the future, 101, sorry, you can send a request back to 0. And here, in the meantime, you want to send requests to 1, 3, 5, and you keep going. And this would take you a grand total of 51. There will this be a grand total of 51 banks. And here you end up, this is going to be 51. 1, 2, 3, 4, 5, 5 and 5. You keep going, it's going to be 50. No, I was right. And you have 1, 2, 3, 1, 3, 5, and you end up with 101 at the end when you issue for 100. And that's when you can issue an access back to 0 in 102, actually, because you want to go to 101 so that you utilize the entirety of your bank, the entirety of your bank parallelism. And what you will notice is that when you go to stride 3 again, you will notice a similar pattern to this. Stride 4 will be a similar pattern to this. Essentially, all the even strides will require 101 banks. All the odd strides would require 100 banks. Let me show you a quick example for this. So let's say we have the bank access order is going to be something like this. You have 0, you're going to have 3, yeah, 6, 9, and you keep going, and you will end up at 99. Then you will do 1 in, well, should it be 99? Yeah, I think it's fine. 1, and then you would have 100, and 2, you would end up at 98. This would have covered up the entirety of the 100 banks, and this will take 100 cycles. At that point, you can issue an access to 0 again. And this again covers up all the 100 banks. You hide the entire 100 cycle latency of accessing 0 by issuing accesses to other banks. So what you will arrive at is that for all odd strides, you would need 100 banks. And for all even strides, you would need 101 banks. And that's how you could solve it, one possible way of solving it. Yes, please. For this one, for the odd stride, first and the third, this one and this one. Do you mean? Is that what you mean? Yeah, we have bank 0. Mm-hmm. Mm-hmm. You are right. I should be taking 99, right? Yeah, you're right. You're perfectly correct. This would be 99 because you count 0 for this 100 cycles later. You can issue an access to the same. You're right. So 100 banks, but you issue a request back in cycle 100. You're correct. Sorry about that. Okay. If that didn't make sense, you can ask me. I will repeat. Okay. And so the second question is here. So, and this is where, okay, so translate the following loop into assembly code that can be executed in the least possible number of cycles in the previously described vector machine. So you want to write assembly code for a C program. What you really need is the instruction set, and we have the instruction set here. I'm going to bring this back here. I think that's visible now. Okay. So you have a for loop. It starts from 0 to 45, and you check if the element in A is 0. If it's 0, you write B to C. Else, C is basically the multiplication of A and B along with A divided by 2. You add them up. And we have these instructions here in the ISA. So let's look at what instructions we have, understand them well, and then come back to that. So the first one is set. And what this does is you have two operands, VST, and a number n. It takes one cycle. And what you can do with this is you can write n to VST. VST in this case is the vector stride register. Essentially, what is the stride that I'm going to use to access the memory for whatever array that you want to access. The second is again a set. And what you want to do here is what opcodes you have here is VLN and the number n. And what you do here is you write the value n to the register VLN, which is the vector length register. Essentially, how many elements in the vector are you going to operate upon? The next is LDM, which I believe there's an description on here. You have one operand VI, where you write the least significant bit of VI to this particular register VMSK, which is the mask register. And we have something about mask register here. So let's look at these two. So the first one, LDM moves the least significant bit, the LSB, of each vector element in the vector register VI into the corresponding position in VMSK. And this takes one cycle. Essentially, this is to build up a mask upon the vector length. So let's say you have vector length 16. The mask register is also sized 16, but you can make sure that, let's say if all of them are 0 except the last one, 1, then the arithmetic operation that you're going to execute will be executed only on the masked element in the vector register. That's what the masking instruction helps you to do. We have already seen VLD and VST. We have VMOL, which takes 10 cycles to perform multiplication. It's pipelined. We add 5 cycles pipelined. We shift right. You can shift right by 1. And then you have V naught. It's perform the bitwise naught of VI and restore it back into VI. And then you have the V compare if 0. So if you have if you compare VJ to 0, and if it is 0, VI will be stored with all ones or all zeros. It's to compare if the values are zeros or ones. All right. So this is what we have in the instruction set, and all of these instructions are going to be useful for us to write down the assembly code. So first, we notice that your for loop goes from 0 to 45, and it's doing so in steps of 1. So your stride is 1, and the vector length is going to be 45 minus 0 plus 1, 46. So you have 46 elements in the vector register. So the first things that you would do is you would set VST, the stride, to 1. You would set the vector length to 46. These are the first two instructions that you will run. You configure the vector machine for the code that you're going to execute. Then you need to check AI conditionally, which means you need the data AI first. And that means that you need to load the data stored in the register, stored in the address that A points to. And let's assume that the location A, the array A is present at location A, which, and the syntax here is the number A here is address, and you want to store them into VI. Let's arbitrarily choose to do this in V1. And this is going to take some time, right? Because you're loading 46 elements into V1. Then the next, while this executes, you can fetch the data corresponding to vector B. So let's do that. We will load that data into B. We'll load that data into V2. We've loaded that as well. And once the data is available for A, you can conditionally check the contents of V1. And to check, and what we want to check here is whether they are 0. And we have the perfect instruction for that. We compared 0. And to do that, we can compare, and we need a VI and a VJ. VJ is the input that we want to compare, which is going to be V1. And let's store this into some other register V3 that we can use to perform computation for this one and this particular one. First, we will take the true condition. If V3 contains ones, which is basically the scenario where V1 contains a 0, then you would basically copy B directly into C, correct? So we need to set up a mask that matches this the compared data in V3. So what you would do is for the mask, you do LDM. So you perform LDM, and what you can, and vmask is an architectural register, so you can just do LDM V3, and this will set up the mask register, after which you can perform the store operation, which stores BI into CI. Is that correct? That is correct. And yeah, you will, and for the store operation, you have the register you want to store, and then the address. The register that we want to store is B, which is in V2. And this will be stored in the address C. Okay. Once this is completed, we want the else condition. And the else condition, again, can be derived from V3. It's essentially the bitwise NOT of V3 when you enter this particular part of the condition. And you can do that by doing V NOT, and you just basically provide the same register, and the same register is overwritten. And that compare register is V3. Then we can again set LDM, set the mask register with V3. And at that point, we can go ahead and compute this. The first step here would be we should divide AI by 2, and then multiply AI and BI, and then you can sum them up and store them into C. But to divide by 2, we don't have a divide instruction. What we do have is a shift right instruction. So we can do VSHA for say. The input here is going to be A, which is in V1. Okay. Then we can multiply, which is let's store it into V5. The multiplication takes two inputs Vj and Vk, which in our case will be A and B, which is V1 and V2, the two inputs here that we loaded in V1 and V2. The result of the two parts are in V4 and V5. So this is V5, this is V4. Finally, we add these two. Let's store into V6, and that's going to be V4, V5, and at this point, we can store the data that's present in V6 into C. Does this make sense? Or not? Okay, I'll assume that made sense. Good. And the last one is the following question. Well, that's the solution. Okay, so what's the number of cycles the previous code takes to execute in the vector processor described in the question? You can assume A and B are in different rows, and the machine has 8 banks, and the rest of the machine is same as part B. Our code from the previous question is here. Okay, so, here. So we need to execute this code, and we need to find how many cycles this would take to execute. And to get the number of cycles for this particular code, we can look at the latencies that we have here. So every instruction has its corresponding latencies. In some cases, they're pipelined, in some cases, they're not pipelined. And they don't necessarily need to be pipelined as well. So let's make a note of all the instructions that we would need to execute. So we have, I will copy these first. So you have the set, you have VLD, you have VST, we compare, we shift right, we mul, and we add, I think in LDM. These are the instructions we have. And they take the following latency. So you have 1, VLD would be 50 or 100 depending on the bank's scenario. Same goes for VST. Compare is 4 pipelined. V naught is 4 pipelined. V shift right is 10 pipelined. V multiplication is 10 pipelined. V add is 5 pipelined. And LDM is 1. Okay, so we don't need this anymore. What we do need is this right here. So clearly the answer would strongly depend on these two parts because they're the bigger values. And what's also interesting is that A and B are in different rows, which means that they will incur row conflicts always. You have 46 elements that you need to access and 8 banks. And we also know from here that consecutive memory addresses are interleaved across different banks, which means that address A goes to bank 0, address A plus 4 would go to bank 1, and so on. Okay, and let's draw out what the scenario would look like at each of the banks. So we have these 7 banks. Okay, The first access is always going to be a miss because everything is pre-charged. So you have a miss. And then you can, after one cycle, you can issue another request to B1. That's also going to be a miss. You keep following this with misses. And I'm going to shorten this and write this as M. Okay. After the miss in the first one, you'd have a hit because the row is already open, right? And this follows here as well. However, we know that our row buffer size is 64 bits, which is really 2 vector elements. Therefore, after a miss and the subsequent hit, you will have to access a different row, which means that you will have another miss for all of these. And I will fill it like this. In total, at this point, we've accessed 8 times 3, 24 elements. But we need 46 elements, which means we can keep extending this until we complete 46. Right? We're going to have another set of misses because this is 32. Here we would have 40 memory accesses done. And this will be 41, 42, 43, 44, 45, and 46. Okay. Your memory access latency for the VLD instruction will entirely depend on the longest running longest running data fetch from the different banks. So B0, let's say, starts at time 0. It will take 6 memory accesses and it will be done here. The longest path here really is the 5th bank because it needs 5 cycles to issue its first load, and then you have the 6 memory accesses, MH, MH, MH. So every V load is going to take 5 plus 3 misses plus 3 hits, which really is 5 plus 300 plus 150, and that evaluates to 455 cycles. Right? And this will be the same for store, because for DRAM, the access latencies are the same. So VLoads and VStores, again, we have 455 cycles. And at this point, we can start drawing out the timeline of what the instructions would look like to find the total number of cycles that we need to compute the code that we were given. So let's start with the 2 set instructions. So you can start with the set instruction first. It's going to take 1 cycle. Then you will have another set instruction. And then you have the VLD. And the question also describes that the processor has an in-order pipeline and issues 1 instruction per cycle. So as long as you don't have an instruction going to the same functional unit, you can keep issuing instructions. In the case of the VLD, you need to issue 46 instructions because you're fetching 46 elements, but it takes much longer than 46 cycles. So this is what let's assume that this is what 46 cycles looks like. And it takes a while for the data to come back. And unfortunately, you cannot issue any more requests in this period, in this blanked out period, because the next instruction is again a VLD, which goes to the DRAM banks, and you will incur conflicts. So the next VLD needs to wait here. And this, let's say, is again, let's call it this. Yeah, this is going to be 46. This is going to be 46. This entire period is going to be 455. And again, you have another length or period where you can't send any other memory request at least for 455 cycles. Okay. And after the VLD instruction, you have the vCompare to 0 instruction, which relies on two inputs. Well, it relies on one input, V1. And the data for V1 is available already at this point. So after the 46 cycles have been spent, you can start the vCompare instruction. And the vCompare instruction takes 4 cycles to start off, and then it's pipelined. So this is the 4 cycles it takes to start. This is vCompare 0, and then it's pipelined for 45 cycles. And it will be hidden behind this because this is 455. It's going to be much longer. Anyway, after vCompare 0, you have the load M, and load M takes 1 cycle. So load M is also nicely hidden behind the memory access latency. Next, you have the vStore. Now, unfortunately, the vStore cannot go ahead until the load M has completed because the DRAM banks are under usage. So the vStore starts somewhere here. Again, you have 46 cycles, and it's going to take some more time beyond that before you can issue other instructions. vNot relies, vStore, and vNot relies on v3, which is again already available. So you can hide it behind this portion here, between the portion where the memory banks are busy. vNot takes 4 and its pipeline, which means you take, let's say, this portion here, it's going to be 4. It's going to be hidden behind the latency, the pipeline. Then you have LDM, which again is going to be hidden behind the various latencies. vShiftWrite relies on V1 and V2, both of which are already available, and they store the data in V5. This, again, you can successfully hide behind all the latency of the vStore. This is about 455 minus 46. Let's say this is 409 cycles. vNot would take 4 pipelined, which means around 4 plus 46, 45. This would be 49 cycles. This is hidden behind the vNot, so we don't need to worry about it. vShiftWrite is also going to be mostly hidden behind the vNot. Again, we don't go beyond the 409 cycles, essentially. That's what I'm trying to convey here. vmul, vadd are similarly going to be hidden behind this portion because 409 is very long anyway. At that point, you need to issue another instruction, the vStore, to finally store the computed v6. And for that, you need to wait until this is completed, the write from the previous instruction. And that is, again, another 46 cycles of instruction issue, and then you hide. Well, it takes time for you to write all the data, the banks. So on the critical path, you have this store the 2 set instructions, the VLD1, VLD2, vStore1, and vStore2. And that's really the result. So the total number of cycles is set 1 is 1, second set is also 1, and then you have 2 loads, 2 stores, each of which are 455 cycles times 4. And this, I will not do the math, computes to 1822 cycles. Sorry for my bad handwriting here. And that's how you solve this problem. Any questions here? Or was this clear? Okay, perfect. And that completes vector processing as well. Should I announce it here as well? Yeah, so we will have, for everyone on YouTube and Zoom, we will have a 10-minute break, and then we'll start again.
Hello, am I audible? Am I audible? Okay. Should I start? Okay. Hello everyone, I am Harshita and I will be presenting 3 questions today. So let's start with the first one, that is Boolean logic circuits. So let's first read the question. During your job interview, you are asked to design a combinational circuit with a 4-bit inputs A, B, C, D, as you can see here in the truth table. So A is the most significant bit and D is the least significant bit, and 2 1-bit outputs. Okay. Is it fine now? Okay. And you have 2 1-bit outputs, fib and G3. And you are given the value of each output is determined as follows. So for fib, the output of fib is 1 only when the input 4-bit number is a Fibonacci number. So as you know that we can calculate the Fibonacci number as the sum of previous 2 numbers. So we will do it. And second, the output G3 is 1 only when the input 4-bit number is greater than 3. So here, as we can see in the truth table, this is written in the ascending order, so we can just write the numbers. So let's first fill the G3 because it's easier. So G3 is 1 for whenever the input 4-bit number is greater than 3. So that is for all of these numbers, G3 would be 1. And for these, it will be 0. And for Fibonacci, whenever the number is a Fibonacci number, then the fib output bit is 1. So let's write the Fibonacci series. Let's start from 0. We are given f of 0 is 0, f of 1 is 1, f of 2 would be the summation of these, again 1, f of 3 would be summation of these 2, 2, and then 3, and then 5, 8, 13, 21. We don't need to go beyond that because here we only have till 15. So 0 is a Fibonacci number, so here it would be 1, and same for 1, for 2, for 3. So 4 is not a Fibonacci number, so it's 0. For 5 it would be 1, 0, 0, and again for 8 it would be 1, and here zeros. For 13 it would be 1, and then rest zeros. So now you fill the missing entries in the truth table as you were asked in part A. And also you are asked to express the output fib in the sum of products representation. So for the sum of products representation, you will pick all the 1 output bits. So you can write it as, okay. So A bar, B bar, C bar, D bar for the first one. And then here, A bar, B bar, C bar, D. A bar, B bar, C, D bar. And then A bar, B bar, C, D. Then again for this, A bar, B, C bar, D. A, B bar, C bar, D bar. And then A, B, C, bar, D. So yeah, I think every item is done. So by this, we are done with our part A of the question. Let's move to the second one. Okay. So in the second question, you are asked to simplify this fib expression that you wrote here using Boolean minimization rules and show your work. So this is very easy. Like we can start with taking the common terms out from this. So we can see that A bar and B bar is there in all of these four terms. So we can just take this out. And it would look like C bar D bar plus C bar D plus C D bar plus CD. And similarly, for the second one, you can take A bar and C bar out. It would be BD plus, sorry, I think it is not there. So yeah, you can't take this out. So this will be there. But from here, you can take, just a second. Okay, so this is AC bar and AC bar. So here you can take the AC bar out and B bar, D bar plus BD. So you will have this, and this term would be 1, as we know, because it has all the combinations of C and D. So you will have A bar, B bar, and 1 plus A bar, B, C bar, D plus A, C bar. Just give me a second. And B bar, D bar plus BD. So from this expression, you can again take C bar out. So you will have A bar B D plus A B bar D bar plus A B D. So if you optimize it further, you will get A bar B bar plus B bar C D B bar C bar D bar plus B C bar D. So this will be the final optimized expression that you will get. Does anyone have any questions? I think this would be easier. And for the C part, you find the simplest representation for the G3 output by using only 2 input NAND gates. So again, you have to show your work step by step. So we haven't written the expression for G3, so let's write it first. Let me put it this way. I hope you can see this. Yeah. So for G3, we will again write the sum of the products form, and yeah. So A bar, B, C bar, D. I will just write it very fast because we have to take all of these values. And then A bar, B, C bar, sorry, let me, yeah, A bar, B, C bar, D bar plus A bar, B, C bar, D plus A bar, B, C, D bar plus A bar, B, C, D plus A, B bar, C bar, D bar plus A B bar C bar D plus A B bar C D bar plus A B bar C D plus A B C bar D bar plus A B C bar D plus A B C D bar plus A B C D. So you will get this long expression which will have 12 terms. So if you optimize it similarly using the approach that we discussed in the part B, so I will just discuss the important part here. So after optimizing it with the same technique used in part B, you will end up with A plus B. So the crux of this question is that you have to represent the output using only 2 input NAND gates. So how will you convert this form into 2 input NAND gates? So since we want NOT, because NAND has NOT and AND, so we can start by taking the NOT of this. And if we write, then these two are equivalent terms. And you can also write this as the complement of A like this. So you can also write this as this, but now it has 2 NOT gates, but we do not have any NOT gates. We only have NAND gates. So you can also write this A bar as A into A, the whole bar. So similarly, we will write here. So now this is, we will need 3 2-input NAND gates. One this, and one for all of this. So this is how the part 3 would be solved. Are there any questions? Okay. I think this is the simpler question. So I will now move to another question. Yeah. So the next question that I will discuss is the performance evaluation. So let's first go through the question. Multi-cycle processor P1 executes load instructions in 6 cycles, store instructions in 6 cycles, arithmetic instructions in 2 cycles, and branch instructions in 2 cycles. So consider an application A where 40% of all instructions are load instructions. So let's assume that we have total of n instructions, out of which load are 40%, so 0.4 of n, and 40% are load, and then 20% are store instructions. So store would be 0.2 n, and then 30% are arithmetic, and 10% of instructions are branch. And we are asked, what is the CPI, that is cycles per instruction, of application A when execute on a processor P1? So CPI is the total number of cycles by total number of instructions. Now what would be the total number of cycles? So we have all these instructions. So let's say if first start with load. So we have 0.4 n load instructions, and each load takes 6 cycles. Now store 0.2 n store instructions, and each store takes 6 cycles. Now arithmetic 0.3 n arithmetic instructions, and each takes 2 cycles. And then 0.1 n branch instructions, and each takes again 2 cycles. And the total number of instructions would be n. So if you solve this, I will not do the math. If you solve this, so you will come out with a number 4.4. So this would be our CPI for P1, processor P1. I hope it's clear. Okay. So second part is totally same. We just have different parameters. So a new design of the processor doubles the clock frequency. So I think we will underline this because this might be needed in the later parts. And however, the latencies of all instructions increase by 4 cycles. So here for all the instructions, it has become now 10, 10, 6, 6. We call this new processor P2. The compiler used to generate all instructions for P2 is the same as for P1. Thus, it produces the same number of instructions for program A. And again, we are asked what is the CPI of application A. It is the same application that was in part A when executed on processor P2. And we have to show our work. So again, we will use the same approach. Like now we will just change the cycle count. I will do it very fast because we don't have much here. And similarly, 0.2n into 10 plus 0.3n into 6 plus 0.1n into 6 divided by n. So again, if you do the math, you will come up with a CPI of 8.4. So there was nothing new in this part. I hope it's clear. Now, in the C part, you are asked which processor is faster, P1 or P2, by how much, like what is the speed up, and we have to show our work. So the speed up is total number of cycles into the clock time. And to find the total number of cycles, we can do CPI into the number of instructions into clock time. So this will be our formula. So, sorry, this is execution time. Yeah. So let's calculate the execution time of processor 1 and processor 2. So execution time of processor 1 would be, the CPI for processor 1 is 4.4. And the total number of instructions, let's assume n as we did. And the clock time would be some time t. Now for the processor 2, let's say it's execution time 2. Again, the CPI 8. The number of instructions are again the same. And so here the time. So here, as you noted in the second part, we were said that new design of processor doubles the clock frequency of P1. So since the frequency is double, so the time, clock time would be half because frequency is inverse of time. So this was the motive of giving that. So now we have both the execution time and we can do the speed up. Let's say execution time 1 by execution time 2. And if you do that, you will get that processor 2 is 1.25x faster than the P1. So this is again simple. You just have to calculate the execution time of two processors and then divide them to calculate the speed up. Are there any questions? Okay. So this is the last part. So here they have asked that you want to improve the original P1 design by including one new optimization without changing the clock frequency. You can choose only one of the following options. So the first is ALU and second is the LSU. So what does an ALU do? An optimized ALU which halves the latency of both arithmetic and branch instructions, and an LSU, an arithmetic load store unit which halves the latency of load operations and doubles the latency of store operations. So what does halving the latency and like doubling it means? So that means we have to do it for processor 1. So if we do the ALU thing, then yes, so earlier the cycles to execute an arithmetic instructions were 2, but now they are halved. So it will be only 1 cycle for arithmetic instructions, and also branch instructions. For branch instruction, it was also 2 cycles. So for branch also, it will be 1 cycle now. And what will an LSU do? it will halve the latency of load operation. That means load will just take 3 cycles, and double the latency of store operation. That is, store will now take 12 cycles. So now you again have to calculate the CPI. So using the same thing as we used here. So 0.4 n into 6 plus 0.2 n into 6 plus 0.1 n into 1 plus 0.3 n into 1 divided by n. And this is when you do the ALU optimization. And when you do the LSU optimization, so CPI will be 0.4 n into 3 plus 0.2 n into 12 plus 0.1 n into 2 plus 0.3 n into 2, and then divided by n. So when you will do the math, you will get the CPI value for both, and wherever the CPI is less, so that will be your choice, because you want cycles per instructions to be less. So this is how you do this question. So this was again a very simple question. I hope everything is clear. Yeah. I think it's, I mean, if you don't do the calculation, you will not get to the answer, and you will have to tell which one you will choose. And if you do the math after writing the formula, then only you can say that this is the answer. So you will have to do it full. So let's move to the third question. This is systolic arrays. Okay. So you are given a systolic array of 2 by 2 processing elements, PEs, interconnected as shown in figure 2 here. The inputs of the systolic arrays are labeled as H0, H1, V0, and V1. And figure 3 shows the PE logic. So this figure 3 shows the logic of each of these PEs. So let's say we treat it as a PE00. So here I1 is the input, which corresponds to the H0, and then I0 corresponds to V0. And this PE performs a multiply and accumulate operation. So it has an internal register reg, and it does the input 1 into input 2 plus the reg value. And then it also outputs the value as O1 and O0. So O0 would be equal to I0, and O1 would be equal to I1. So each of these P's will do this. So this O1 would go to then PE01 if we assume that this is a design of PE00. Yeah, so figure 3 shows the PE logic, which performs a multiply accumulate MAC operation, as I already explained, and saves the result to an internal register's reg. Figure 3 also shows how each PE propagates its inputs. This also I explained. So we make the following assumptions for this. The latency of each MAC operation is 1 cycle. So to perform this, we need only 1 cycle. That is, if the inputs to the PE are available in cycle C, the updated register value will be available in cycle C plus 1. The propagation of the values from I0 to O0 and from I1 to O1 takes 1 cycle. So this also takes 1 cycle, and this also. And the initial values of all internal registers is 0. So this will be set as 0 initially. Now your goal is to use the systolic array shown in figure 2 to perform the multiplication C is equals to A cross B, where A, B, and C are 2 by 2 matrices. So let's write this, because to solve the further question, we will need to see it. So let's say matrix A00, A01, A10, A11. And it has to be multiplied by the matrix B, B00, B01, B10, B11. Okay. Where A, B, and C are 2 cross 2 matrices. Recall that the multiplication, so this is how, they are telling you how to do the matrix multiplication. I think you all know this. So as an example, for k is equals to 2, the calculation for C00 is shown as follows. So let's say the resultant matrix is C. So C00 would be A00, B00 plus A01, B10. Again, C01 would be A00, B01 plus A01, B11. I'm writing this because you will need this. So C10, A10, B00 plus A11, B10. And lastly, C11, A10, B01 plus A11, B11. Okay. So now we have to compute the multiplication in the minimum possible number of cycles. So fill the following table with each input element from matrix A and B in the correct cycle and input port, so of the systolic array. Each output element for the matrix C in the cycle and PE that generates each output. So whenever the output is generated, like C00, C01, we have to fill it in here. So part A says we have to fill in the blanks only with relevant information, and input cells left blank would be interpreted as 0. So let's start. So let's say this PE00 has to calculate C00, PE01 has to calculate C01, PE10 has to calculate C10, and PE11 has to calculate C11. So to calculate C00, first we need A00 and B00. So first we can pass A00 from H0 as an input. So here we can write A00. And as V0, we can pass B00. You can also do vice versa, like pass A00 as V0, and then your table will look a bit different, but I will go with this. So in the first cycle, you can only do this. And when these inputs will go inside the PE, so it will have a register, and the register initially is 0. So it will become input 1 into input 2 plus 0, because it was initially 0. So we didn't get any output out of these 4 in the first cycle, so we will leave these blank. So next, let's move to the next cycle. So here, these in C00 would be propagated to PE01, and it will calculate C00, C01, and the rest later. And similarly, this B00 will be propagated here, and similarly, it will also calculate the MAC operation. Now, what will be the new inputs in this cycle? First, now PE00 calculated this. Now it has to calculate A01 and B10. So as H0, we can pass A01, and as V0, we can pass B10. In this cycle, this PE01 has also received an input from PE00, so we will also pass another input from V1. So what PE01 has to compute? So it has to compute this. So it already has this, and it needs this, B01. And it also needs A01 and B11. So in this cycle, as V1, we will pass, sorry, this will be 10 because we have to pass it here and it has to compute, and this will be B01. and as H1, so it has to compute C10. So A10, B00, A11, and B10. So here we will pass this A10 because it already has B00. So now this PE00 has all the outputs that it required, like this from the previous round. And in this round, we passed A01 and B10. So this previous cycle's reg value will be added here, and it will have the full C00. So that will be in the next cycle because this will take one cycle, this will take another one cycle. So after 2 cycles, PE00 will have C00. Now similarly, now if you see, we needed these outputs. Basically, we needed 8 inputs. A00, A01, A10, A11, and B00, B01, B10, B11. We have already passed A00, B00 in the first cycle, and A01, B01, A10, and B10 in the second cycle. Now we are only left with A11 and B11. So which all PEs require this? So this PE01 requires B11. So we will pass B11 here as V1, and these PEs require A11. So we will pass A11 as H1. So now we are done with all the inputs, and now this so here the operations that didn't require A11 and B11 would be done in this cycle. So that is C01 and C10, and then in the next cycle we will have C11, that will be A10. So this is how we will construct our table. Yeah.
Just one question in the
This one? Yes. Yes.
Should there in that cell be A00 times B10?
Yes, so if you want, you can write it, but I didn't write it because in the question they have asked you to write the full output when you get that. So the output bits are only C00, C1, C01, C10, and C11. So that's why I wrote only this. But if you want to keep track, if you also write A00, B00, that will not be wrong. Yeah. So, okay. Now we have one more part for this. So the question is, suppose that the same systolic array from figure 2 is used to compute the multiplication of two 4x4 matrices. How many cycles does it take to perform the multiplication? Assume that the register in a PE resets to 0 immediately after an output is generated. That is, PEs can start accumulating for the next output element in the next cycle without waiting for an extra cycle to reset the register 0. So you don't have to waste a cycle to reset the register 0. That's what this says. So we can do it with unit method. So in part A, we had a 2x2 matrix, and it has 8 inputs, 4 for matrix A and 4 for matrix B. Now in this case, you have 4x4 matrix. So you will have 32 inputs, 16 for matrix A and 16 for matrix B. So how much time did it take in part A for us to supply all the inputs to the PEs? It took us 3 cycles, right? So here we can see that 8 inputs took 3 cycles. Then 32 inputs will take 3 into 32 by 8. that is 12 cycles. So 12 cycles will be required to supply the inputs. So let's write 12. So this is the first thing. Now, when you had to calculate, let's say C00, so you had 4 elements, like 4 input elements were required. But now, since it is a 4x4 matrix, you will need 8 elements. I can write it. A01, B10 plus A02, B20 plus A03, B30. Now, here we can see that in the case of 2x2 matrix, you got the first output after 2 cycles. So when you had 4 inputs, like basically you had to compute on 4 operands, then it took 2 cycles. After 2 cycles, in the 3rd cycle, you got the first output. Now you have 8 operands, so it will take you 4 cycles. And in the 5th cycle, you will get your first output. And also you can also see here that after you get the first output, you need 2 more cycles to get all the output. So this trend will be repeated after this. So first we can add, so earlier we got 12 cycles. Now after that, after 5 cycles, sorry, yeah, so 4 cycle, on 5th cycle, you will get the first output, and again 2 more cycles to get all the outputs. So if you sum this, it will be 19. So here the answer would be 19 cycles. So, any questions? Yeah, so to look at it, I mean, I don't have an intuition, but if you will calculate it, then I can show you the table here. So this is how the table will look. So because the PE structure has not changed in this, so you can only supply like 2 inputs at time, and again you can supply the same number of inputs. So if the number of inputs have increased, then it will take n into the inputs that you can supply number of cycles to feed in all the inputs, right? So that's why it is scaling this way, if you can imagine. But otherwise you can try constructing a table again, and it will again take a lot of time. But yeah, this is how you can see. But yeah, you can relate it with how many inputs you can feed and then scale it. And if the PE structure would have changed, then yes, you would have to see it in a different way, because now you can feed in more number of inputs, so it cannot scale linearly like this way. Yeah. Any other questions? Okay, so that's from my side.
Wait. this way? Okay, cool. Okay, can you hear me? Cool. So we're going to start with VLIW. Should I just read this, all of it, or just description? Okay, so let's just run through this quickly. So we have to compile some VLIW code by hand. This particular CPU has 7 functional units, 3 load units, 1 store unit, 1 addition unit, 1 multiplication unit, and 1 branch unit. So the VLIW can only execute the instructions, the operations shown in table 1 here. And the table also shows the semantics of each operation. All assembly operations have 1 cycle latency. We have 32 registers, we won't need that. The registers are read at the rising edge and written at the falling edge of the clock. And the memory is word addressable, 1 word equals 4 bytes, and the VLIW processor operates at 1 gigahertz. So figure 1 shows some C code. You can see here, basically, exactly the loop that we're most interested in. And also the associated assembly code for this particular C code. Registers R29, R30, and R31 hold the base addresses of the C code arrays A, B, and C. And register R0 is initialized with 0, and register R1 with 1. So my job here is to compile the assembly code into VLIW instructions to schedule them statically. So we're going to fill this table with, how am I going to do this? You have to see both. Cool. To fill this table with the instructions showed here. So if you remember correctly, this machine has 3 load functional units, and the first 3 instructions are load instructions. There are no dependencies between these instructions, so we can load them. We can schedule them at the same time. So we will have the load 1 inc here. I'm not going to write the details of this because I can't fit it, but you should. Load. And also the other load, this one here. So we have a multiplication with R2 and R3 after that, but we cannot schedule this because this depends on the result of these operations. So we are just going to fill the rest of here, this with NOPs. In the next step, these operations will have completed because every operation takes 1 cycle latency. And we will be able to schedule the multiplication over here. So this operation goes to the multiplication unit. And the next operation depends on this. So you can see it's add R6, R5, R4, and we are calculating R5 here. So this cannot be scheduled in the same cycle. So I fill everything else with knobs over here. After that, we have the add. Add also depends on R5 because you can see it's add R6, R5, R4. So I'm going to schedule the add here and fill everything else with knobs. Stores the result of R6 in the next cycle because R6 depends on the calculation of add. Is the store unit here. It's store inc, and the rest are knobs. And we cannot schedule the branch in the same cycle because this is a store inc. It increments R6. You can see here that it increments R1. So that means that there is a dependency over these instructions. And you have to schedule the branch in the next cycle, B, N, E, and the rest are knobs. So this is the table filled out. Let's move on to B. What is the ratio between the number of useful operations and the number of VLIW instructions in your code? A useful operation refers to any assembly operation that is not an op. So here, as you can see, it took us 5 cycles to schedule everything, and we had 7 operations to schedule. So the result here equals 7/5. Yeah, that's it. What is the execution time in cycles of the VLIW processor when executing the sequence of instructions in table 2 as a function of the loop counter n? Show your work. And this is very simple here. You know that each loop will take 1, 2, 3, 4, 5 cycles, and it's going to repeat for I equals 1 to I equals n, I smaller or equal to n, with an increment of 1. So it's going to repeat n times. So that means that in cycles, this is 5 times n. Yeah. Sure. Better? Yeah. Any questions on this question? No. So let's move on to the next one, which is about caches. Consider a processor using a 4-block LRU-based L1 data cache with a block size of 1 byte. We are going to start with an empty cache, and an application is going to access 3 cache blocks with the following addresses, 0, 2, 4, in the given order. A malicious programmer tries to reverse engineer the number of sets and ways in the L1 data cache by issuing only 2 more accesses and observing the cache hit rate across these 2 accesses. Assume that the programmer can insert the malicious accesses only after the above 3 accesses of the application. So we are going to add 1 more access here and 1 more access after that here. And we're going to observe how this changes the cache hit or miss rate. What are the addresses of the next 2 cache blocks that should be accessed to successfully reverse engineer the number of sets and ways in the cache? There may be multiple solutions. Please give the lowest possible addresses that can enable the identification of the number of sets and ways. Please explain every step in detail to get full points. Okay. So we have a 4-block cache, and that means that there are 3 possible cache configurations. The first one is the one-way associative cache or direct map, and this is going to have 4 different sets. So let's name this configuration A, and this is set 0, set 1, set 2, set 3. The second configuration is the 2-way associative version of this. So we have 2 sets with 2 ways each. This is configuration B. So this is set 0, set 1. And here we have inside here way, let's say W0, W1. This is 1. And for the other set, also way 0, way 1. Excuse my terrible handwriting. And the other configuration is C, which is basically a fully associative cache, since we have 4 blocks and it's going to be 4-way associative. So basically, this is just one large set with way 0, way 1, way 2, way 3. That's terrible. And we're going to place for each of these caches these blocks in here. So in configuration A, 0 goes, of course, to, this is in binary 0, 0. This is 1, 0, and this is 1, 0, 0. I'm going to add an extra bit in every one so we can distinguish. 0 goes here. 2 goes here. Let me see. Got confused for a second. And 4 is going to evict 0, and we're going to be left with 4 here. So for B, 0 is being placed here. Then 2 is going to reside in the same set as this one over here. And 4 is going to evict the least recently used, which is 0. And it's going to reside here. And for C, we don't have any conflicts. So 0 is going to go here. 2 is going to go here, and 4 can go here, for example. So we have to find X and Y so that we can distinguish between all of these. There is no use in trying to issue any other memory accesses for addresses other than 0, 2, and 4, because these are going to miss anyway. They're not in the cache. How we have to find this out is by causing conflicts between elements and then observing how the miss rate changes. So I'm going to start by issuing 0 in every one of these caches, trying to store 0 or load 0. Let's say that load 0 and see what happens. So 0 is going to conflict with 4 over here. It's going to evict it. So we're going to have, let's say, 0 evicting 4. How am I going to write this? And over here, way 0, way 1, way 0, way 1, S0, S1. So here, 4 is also going to evict, 0 is also going to evict 2, because it's the least recently used one. And here, nothing is going to be evicted because this will hit in the cache. So I'm not changing this at all. And now I'm going to issue a load on the 2. And what is going to happen here is that the 2 in this case is going to hit. 2 hits. In this case, it's going to miss because it's not in the cache anymore. And here it's also going to hit. So for this configuration, for the C configuration, we hit both on the 0 and the 2. That means that it has 100% hit rate in the cache. For the B configuration, we missed both on the 4, on the 0 and on the 2. So that means that we had a 0% hit rate. And for this configuration, we had a miss on the load of 0 and a hit when we loaded 2. So that means that we had a 50% hit rate. So you can clearly see that with this access pattern, we can distinguish between the 3 cache configurations, and we can reverse engineer which one this is. Any questions? Yeah. Yeah. What do you mean? Yes. No, this is byte addressable. These are not like, it's a memory address of 0. Yeah. So you load the 0th byte of memory, then you load the 2nd byte of memory, then the 4th. Yeah. Moving on to B, what is the number of sets and ways if the cache hit rate observed over the 2 extra addresses in part 1 were 100%, 50%, and 0%? So here, I have to say, there is an alternative solution here that uses 0 and 4 instead of 0 and 2. But this is not the optimal solutions because we were looking for the lowest possible address that you can use. So that's why here you have to fill in your results based on what you did in the first step. That's why we ask this. So let's say that we selected the 0 and 2 access pattern. So if we have 100% hit rate, that means that we have the fully associative cache. And that means that we have 1 set with 4 ways. If we have a 50% hit rate, that means from the previous answer that we had the direct map cache. So this here has 4 sets with 1 way. And for 0%, this is the two-way associative cache. So 2 sets, 2 ways. And that's it for this question. Moving on to C. Is it possible to reverse engineer the number of sets of ways of the cache using 2 accesses after the application's first 3 accesses, if instead of LRU, you used the MRU policy? So the most recently used cache block is getting evicted when you replace something. And the answer to this is no. Why is it no? So let's go over this again. We have our configuration A, our configuration B, our configuration C. Don't need any ways here. And after the first 3 accesses were issued, this is going to look like 4 and 2. This is going to be 4 and 2 in two different ways of the same set. And this is going to be 0, 2, and 4. So again, if you try using any other addresses 0, 2, or 4, nothing's going to happen because you cannot. These are all going to miss in the cache. So you have to work with these three. If you issue 0 or 2 or 4, anything is going to hit here. So you can clearly find out if this exists. But the problem is that if you try to issue 0, for example, then in this case, 0 is going to evict 4 over here because it can only go into this set. Then here, 0 is going to evict 4 again because this is the most recently used. So you cannot reverse engineer anything anymore because these look identical. They only have 0 and 2 inside. So the answer here is no. As we said, you cannot reverse engineer the cache with this. And the problem here is that eventually everything looks the same. Any questions? And finally, there is the prefetching question. So we have two programs, A and B, that run on two different toy machines, M1 and M2, to determine the type of the prefetcher used in each one of these machines. The programmer observes the following memory accesses in the program, and we have the following metrics for coverage and accuracy. And coverage basically is the fraction of the program's memory accesses that were correctly predicted by the prefetcher, and accuracy is the fraction of sent prefetch requests that are used by the program. And this is the table as I showed previously. There are three prefetchers that we're going to evaluate here. One is a stride prefetcher. The other one is a first next block prefetcher with degree 1, which fetches the next block after an access to a particular block. And then there is the fourth next block prefetcher with degree 1, which will fetch cache line A+4 after an access to block A. And here there are some assumptions. Each prefetcher has a large enough resources to detect and store access patterns. Each prefetcher starts with an empty table. Each prefetcher sends only one prefetch request for each program access. Each memory access is separated long enough in time so that all prefetch requests sent can complete before the next access occurs. No prefetcher employs any confidence mechanism. The stride prefetcher will send a prefetch request to address A+4 by only seeing two consecutive memory accesses to addresses A and A+2. So basically, what we have three prefetchers, two machines with these metrics, and we want to find out which prefetcher each one of these machines uses. There are two ways to go about this. There is the hard way, and then there is the smart way. I'm going to show you the hard way because it's actually too much work. If I can find it. Konstantina, I don't have the. Yeah. For the prefetching. Ah, here it is. Yeah, thanks. Sorry. So the hard way is to take these accesses, all of them, and evaluate every single one of these prefetchers and see what they're going to issue, measure the coverage for both of these programs, and try to find it out this way. You are going to calculate the coverage and the accuracy, and eventually what you will come up with is that M1 is the fourth next line prefetcher, and M2 is the stride prefetcher. And that's the hard way. But the smart way here is to see that, as you can, accuracy for M2 is 499 out of 500, whereas for this, it's 499 out of 501. So here and here. Of these prefetchers, only one needs to wait for the second access. And that is the stride prefetcher. So as you can see in the solution, the stride prefetcher is M2. And you can see this here. In the it issues one less access in total. So that immediately gives you the result for machine 2. For machine 1, what you're going to see is here that let's try the first next block prefetcher with degree 1 on program B. So this is going, we have access to B, B plus 2, B plus 4, basically B plus even. So the next line prefetcher is going to fetch always B plus odd, right? B plus, let's say 2K plus 1. That's odd, always. So if machine A had this prefetcher, the next line prefetcher essentially, we were going to see an accuracy of 0 because all these accesses are even and this is an odd address. So it cannot be this. It has to be the fourth next block prefetcher with this with degree 1. Does it make sense? Cool. There are no other questions for this particular question. So I think we're done. Hmm? Yes. So we have a question for VLIW online.
No,
Ah, no,
we're done.
we're done. Okay. What do you want?
No, I'm just checking that you did all three because it was too fast.
I did all three. Yeah.
Then now it should be Atterberg's turn.
Yeah.
So here Atterberg is going to join online and solve the very low question for us. Let's see. Ataberk, can you hear us?
Hello,
Yes. Great. Okay, so
can you hear me as well? Okay, you
yeah,
can
we
hear
can
me.
hear you.
Can you see the screen?
Not yet.
Yeah, nice. I'll figure it out.
Yeah, no worries.
Okay. I joined the wrong Zoom, so I'll correct that.
But I can see you in
No,
the
no,
correct.
I joined with my other device.
Okay then. You are co-host, so it should be fine.
Recording in progress.
We can't hear you if you're talking.
I am not talking. I'm still trying to find the correct Zoom link. Sorry. I found it once. I think I can do it again.
Progress.
Now I think it works. So let me share my screen quickly. Oh. Can you make the other Ataberk also host or whatever?
Okay, I think we're good now. You can try sharing.
Mm-hmm. Yeah.
Yes, we
There
can
is
see the screen.
Oh, there you go. Okay.
Do you
I will
guys see
zoom
this
in a
okay, or
bit.
should he zoom in? I think maybe you need to zoom. It's too vertical right now. That's better, yes.
It is too vertical. Wait.
Now it's good now.
Hold
Ah,
on.
yes, now it's even better.
Okay. So yeah, we will solve the Verilog question from 2 years ago, I think. And it says analyze the following Verilog module and answer the question. Assume that the input has always this value, and that's 9. And you're asked to find out the values that the out signal gets in the following 10 cycles, basically. So here, if you look at this circuit for some time, you will figure out that it's doing something like it's outputting the numbers in the Fibonacci sequence. I won't get into the details of why unless someone asks a question. I'll just basically I'll be walking you through the answer. So here, another key thing is that we won't output the Fibonacci sequence number until a control variable, that's variable 4, equals n. So if you look here, you'll see that n is always 9, but variable 4 or var 4 starts from 0, gets incremented every cycle. So what we'll see is variable 4 until variable 4 becomes 9. And the first value that variable 4 takes is 0. So this will be like 0, 1, 2, 3, because it's incremented by 1 every cycle, until it gets to 9. And if you actually compute variable 1, 2, and 3 for 9 cycles, you'll see that this at this cycle, variable 3 will have 55. So that is basically it for this part of the question. And as an explanation, you can put something like the module outputs the number in the Fibonacci sequence, and the index of the number is basically the cycle we're currently at. Do we have any questions about this? I can't see the room.
No, Ataberg, they're good.
Okay. So this is relatively easy. And the second part of the Verilog question is a bit more wordy. You have what's claimed to be a ChatGPT generated code. Probably today this would look much better. This was 2 years ago. It says that a Verilog module that simulates a character's movement on a 2D plane. Then we have like basically the specification of the module. It takes 4 inputs for 4 directions in the grid that the character can move to, and it outputs the coordinates of the character. If none of the direction inputs are set, this is critical for this question, the character stays at the same coordinate, so it won't move. And the initial coordinates are 0, 0. And we have also a variable called stride that determines how many units the character moves in one step. So if stride is 0, we expect, or if stride is 1, we expect something like, okay, if basically, let me just put it this way. So stride is 1, the input is left. Let's say left is true. I'll say true, what you understand what this means. If you're in 0, 0, we expect you to go to something like -2, 0, right? So you're skipping 1 grid element. All right. So first, we're asked to provide our choice for each of these bullets and 1-line expression for 3. So I'll do them one by one, and I'll try to explain why I choose a certain option. So the first one is going to be an input wire, 3 bits. So this is a 3-bit vector. Why? Because it basically stride should be declared as an input because it's specified as an input to the circuit. And this basically is not a valid syntax, right? So this you cannot put anyways. So the only valid option really is C. So that also tells us that the stride can be 3 bits. Sorry, 20, yeah. And the second one is this. And the reason why that is basically the other ones are wires, but in this always block, we make assignments to this variable x internal, y internal. So that's this line, for example, and this line. So for us to be able to make assignments inside the always block, these needs to be defined as regs. And the third one, I'll write the full expression, and then I'll explain what it means. So we're checking if stride is not equal to 0. So this 3 comes from here. Then it's stride, if not, it's 1. So its stride cannot be 0. And then why? Because, I mean, what does this do? It's a ternary operator. So it's like, if this is correct, then you take this value. If it's not, then you take 1. There's a semicolon at the end. And you have this same syntax if you look in the first part of the question. So you could, in theory, if this was your exam question this semester, you could look at the other question and get a hint. And the last one is going to be a sign, because, I mean, you cannot put nothing there. That wouldn't be correct. You cannot put equal, the equal or the equality check operator or let. We didn't even cover this. So this is wrong, this is wrong, this is wrong. Only this can be put there, and that's the correct thing. Do you have any questions here?
And no, they don't have any questions at the book.
Cool. Then the last thing is asking if ChatGPT injected any errors in this code. Technically, it didn't anyways, because ChatGPT didn't write this code. But assuming that the question is correct, you should basically notice a logic error here, line 18. The specification says that the character shouldn't move if none of the buttons are pressed. But here, no matter what I do, unless the reset signal is set, my character will move in the X direction, in the X direction by some amount. So this shouldn't have happened. And that's the sort of the bug in this code. And I think that's it.
Okay. Any last questions from you guys? Okay. Okay, thanks a lot, Ataberk.
Yeah.
It was clear. Thank you for your time. Yeah, so that was the last one, guys. So we're going to now finish the session. If you have any questions, feel free to reach out to us. Send an email, or yeah, probably an email will be good. And I hope you have a good studying session and prepare well for your exams. Also, don't forget that we have planned some premiering of other problem-solving sessions. It's going to be happen next week from Wednesday to Friday, but they will also be online for you to see when you are like more convenient for you. Okay, thank you.